We start with the first one. The first speaker is Didier Auroux from Nice, and he's going to talk about diffusive back and forth nudging.
Okay, so thank you. So first I would like to thank the organizers for this nice school and probably a very nice conference too. So thanks to Amit and Chris. So what you can see on the picture was the mathematics department in the university for okay. So this was the mathematics department up to probably 15 years ago, and as this is the most beautiful building in the campus, the administration just took it. So now we have a new building somewhere, but in case you come in Nice, you will see that we have a very nice campus. So basically I will present the back and forth nudging algorithm. So I should apologize because most of you have already heard at least a part of this talk. And then the version of this algorithm. So the motivations for simulation are the following. The idea is that when you study geophysical fluids or environmental problems, either you have a poor modeling or quite few observations, and it's difficult to forecast the evolution of the system. Then you have also some problems with chaotic systems or turbulent systems. So the idea of data assimilation is to combine the observations and the models so that you can improve the knowledge of the system and try to identify either the initial condition or some model parameters, try to estimate the solution with usually the goal to have a reliable forecast of the system. So for instance, just weather forecast. You want to know if tonight it's going to rain or not. So actually, you have a model which has the evolution in time. So if you give the initial condition, you can just compute the solution and find the forecast. And then you have some sparse observations that are usually very noisy. And the idea is to combine the model and the observations to find the best state, the best solution for your system, and then you will be able to compute some reliable forecast. Okay, so as I am the first speaker, probably I should explain how data assimilation works. So I have a funny scheme. So you start with an oversimplified model and with sparse observations. Then you make some over-optimistic assumptions about the observation errors. And for the model, you have probably to make some irrelevant assumptions about the model error too. And then you get some optimal analysis that is way too expensive to compute. So you have some problem. So you try to develop something on a highly idealized situation, some toy models. Then you add some mathematical stuff. You can add also some probability and statistics because it's even better. And then you can apply a simplified estimation method, but you require some hypotheses that are almost never satisfied. Then you switch to the computer tools. So you add some, probably you had many coding errors. You also have bad numerical approximation. And at the end, you get usually an analysis that is both worse than the model and than the observations. So that is your main problem. So you get confused. So So you may ask for management directives, you may ask some other people, what should I do? They will try to say, okay, you should create something else, produce something, and well, at the end you are stuck in this loop, so you are still confused. So you add some complex features to the algorithm, but anyway, you're still back here with bad analysis. So you just force the agreement between the solution and the observations, so that at the end everything works. You change the acronym for the assimilation system, and hopefully you can get some publication. So this is basically how data assimilation works. Okay, so let's get back to serious things. So nudging. If you assume that you have some model that you can write as this equation, so it could be a system of ordinary differential equations, or it could be partial differential equations, so it could be partial derivatives here, and F is your model. So you have some initial condition, for instance the background state. Then, on the other hand, you have observations of your system, and you need an observation operator to make the link between the observations and your system state. So the standard nudging consists in adding a feedback to the observations inside the model equations. So you simply nudge towards the observation state. So you use the difference between the observation and the corresponding quantity computed from the model. And K is some gain matrix. And hopefully at the end, when you run this model here, whatever the initial condition is, your hope is that the X will converge towards the observations. So in the linear case, this is very well known in automatics as the Luyện-Berger asymptotic observer. So there has been many studies about nudging and data assimilation for weather forecast, ocean forecast, and it was probably the very first data assimilation scheme. And then some people try to optimize the nudging coefficients. So there has been several recent work, and also our colleague Lakshmi Varahan that will give some talk this afternoon, I think. So on a linear situation, if you assume that your true solution is a solution of the system, of the model F, so X true is a solution of dx over dt equal fx, and you assume that you observe this particular solution without any observation noise. Then you compute your nudging state with the feedback to these observations. And the idea is that if you compute the difference between the two solutions, then it is the evolution in time is given by the matrix F minus KH. So the model plus the nudging term, the feedback. So if all the eigenvalues of this matrix are negative, then this quantity will decrease exponentially in time and converge to 0. It means that your nudging state X will converge to the true solution X true. So the idea of the following is that the standard nudging works if you have a quite long assimilation window, because you have some asymptotic convergence. So if you work with a finite, a quite short assimilation window, then it will not converge to the solution. So from your final state that you obtain with the standard nudging, the idea is to come back to the initial time. And the easiest way to do that is to use the background model. So simply it's the same model equation, but with a final condition, and you have to solve it backwards in time. So usually this model is, the background model is unstable, so we can try to stabilize it with some feedback to the observations. So we can add a standard nudging term to this backward model. And then, after solving this, we are back to the initial condition, and we have another initial condition, a new one. And we can iterate. And this is the back and forth nudging algorithm. So you start from the background state, for instance. You solve your model forward in time with the feedback to the observations. Once you are at the end of the assimilation window, you solve the backward model with also the feedback to the observations, and you are back to the initial condition. And then you can start again forward, backward. So the idea is that if your forward and backward solutions converge towards the same limit, so you assume that here you have x, the limit, and here also, then you can compute the sum and the difference of these two equations. So if you take the sum, then you will get that dx over dt is equal to f of x, and this disappears. So x is a solution of the model. And if you take the difference, then you will get that this term here is equal to 0. So it means that your state perfectly fits to the observations. So how to choose the nudging matrix K? So for the forward model, there is a variational interpretation. So if you discretize the model equation like that, so you assume that you know your solution at time n, and you want to compute the solution at time n plus 1. And so the solution at time n plus 1 is a solution of this equation here, and it's also the minimum of this variational formulation, which is nothing else than the sum of the energy of the system and the quadratic distance to the observations. So if you choose this particular gain matrix with the inverse of the covariance error matrix for the observations, times the transpose of the observation operator, times some scalar coefficient if you want, then you minimize, it's a compromise between the energy of the system and the distance to the observations. So this is exactly the same quadratic distance to the observations as in the 4D var. Then for the backward nudging matrix, the idea is that first you should stabilize your model, because without nudging usually it's unstable. And then also try to make the feedback to the observations. So in a linear situation, if the system is observable, then there exists a matrix K prime such that your backward model minus f and the nudging minus k prime h is a stable matrix. So all the eigenvalues are strictly negative. And then your system is stable and you have the feedback to the observations. So this is usually difficult to compute because you need to solve a Riccati equation. So a simpler solution is to choose something almost like the 4-1 matrix, which is another coefficient times h transpose r minus 1. And then you have to tune this coefficient. So usually you can take the smallest value that makes the backward integration stable. Because if you take k prime equal to 0, probably you will have no nudging, so your backward model will probably be unstable. So you increase until you have some numerical stability. So just one slide on theoretical convergence results on viscous linear transport equation. So the equation is there, you have the transport here, you have some diffusion, and then you add the nudging term for the forward model and for the backward model here. So the idea is that after k iterations of back and forth nudging, the initial condition error here is given by this exponential times the initial error on the initial condition. So the error decreases exponentially thanks to these, let's say, positive coefficients. So either you can increase your nudging coefficients, then at the limit you have some infinite feedback to the observations. So it means that you simply replace your model state with the observations. so it's not very physical. Either you can take an infinite assimilation window. So this is the asymptotic observer. So this is nudging. Or the idea is that if you want to keep some physical problem, well, you don't replace your model state with the observations, and you work with a finite assimilation window, quite short time assimilation. Then you increase the number of iterations, and if you, the limit, if you take an infinite number of iterations, then this will decrease asymptotically to 0. So you will identify the true initial condition. So some numerical experiment on a shallow water model. So it's a 2D model with the sea surface height and the two components of the velocity. So everything is in a square ocean. So you have the Coriolis force, you have some wind stress and dissipation. And so I don't know why the mouse is not working very well. Okay, so let's do it like this. Okay, so this is, for instance, the sea surface height with the ocean here, and you have some circulation. The water is going like that, and then you have a double J recirculation on the north and on the south. So this is a very simple model, for instance, for the North Atlantic Ocean. And so we use twin experiments. So we generate the observations from a reference run. We extract some observations only on the SSH. Every 5 grid points in space and every 24 hours. So we have almost the same distribution as satellite observations. So the assimilation period is 15 days, and then the forecast is 45 days. We use wrong initial condition for the background state, and so we can try to assimilate the observations. So I just stopped. So this is the wrong initial condition, and you run your model with forward and then backward resolutions with the nudging. So you can see probably that it's going on the east side, and then it's going backwards in time. So you can see 5 iterations of the ocean going forward and backward. So this is represents almost the Gulf Stream. So you assume that it's quite hot water going from the east coast of USA to Europe, and then during the backward integration, you just send back the water to USA. So after 5 iterations, the state almost converged, and we are back to the initial condition, to the initial time. So we can compare what we obtain with the true state. So this is the true initial condition. This is the background state that we used to initialize the algorithm. And this is what the 4DVAR does with 5 iterations, because we can almost compare these two algorithms, because they both consist in solving forward and backward systems. So in the 4DVAR, it's the direct model and the adjoint model. So here it's the forward and backward model with nudging. And then from all these initial conditions, we can use the model to make some forecasts. So after some time, so at the end of the assimilation window, after 15 plus 45 days, this is what we obtain. So we can see that what we get here is quite close to the true state, except for the position here of the Gulf Stream. So this is not exactly the correct location. If you don't use data assimilation, then your forecast is completely wrong. And also the 4DVAR, if you stop it after only 5 iterations, it's not very good. So you need probably almost 20 iterations to get something quite reasonable with the 4D var. You can do the same with the velocity. So here's the first component of the velocity. So you can see water going like this in the backward, and in forward mode it's going like that. So there is no correction on the velocity here, but as the height is corrected and the system is coupled, then the velocity is somehow corrected. So here also 5 iterations, and then we can compare with the other initial condition, the true one, the background, and the 4D var one. So one more iteration. So the first time I did that, I showed to the guy that originally writes the direct code. I showed him the water going to the left. He said, "Oh, that's not me. It should." I think there is no bug inside the code. So here is the true state. You can see that the current is almost at the correct location. Without data assimilation, it's not, well, it's quite good here, but here it's not. And with the 4D var, we have still some waves that haven't disappeared yet. So after a few more iterations, everything disappears. So you can see that after some time during the forecast, it's still quite good. It's almost reasonable also for the velocity. So here, so we compare the relative difference between the true solution and the forecast solution. So here's the assimilation window, and here the forecast 45 days. And so the back and forth nudging is here. So usually the initial condition is not very well estimated because it comes from a backward integration, which is not very stable. But then as you corrected the solution along the unstable modes, then the error decreases quite sharply when you use the model to make some forecast. So here's the 4D var after 5 iterations, so it's not very good for a forecast. The 4D var with 16 iterations, so here you can see that it's much better than with 5 iterations. But the point is that instead of doing 16 iterations of 4D var to get the convergence, you could, for instance, perform 2 iterations of back and forth nudging, get a new initial condition, a new background state that you can use for the 4D var, and then run 3 iterations of the 4D var, and you are here. So you get almost the same thing as 16 iterations of 4D var. So here you can divide by 4 or 5 the computational cost to get almost the same solution. So the idea is that the back and forth nudging converges very quickly with very few iterations, so you can run some iterations and then get a better initial condition and then use it for 4D var or Kalman filter. So a few words about diffusion problem, because it is well known that if you have some diffusion and if you consider the backward model, then you have some trouble. So for instance, just consider diffusion. So we have the heat equation. The backward nudging model will be like this, with the nudging and the final condition. So if you change the time variable to get back to a forward model, then you get this equation. So you have the nudging term, but you have a diffusion term with the wrong sign. So this is an issue because you can just get an infinite solution in a very short time. So the idea is that the spectrum of the Laplacian is unbounded theoretically, but then numerically it will be bounded. But still, if you want to stabilize this, you have to take a large value for k, and then it's simply, you just forget the physical model, because you just forget the Laplacian. So theoretically, there is a problem with diffusion because, for instance, viscous linear transport equation or Burgers equation, if you don't observe everywhere in space, then your backward model is ill-posed, whatever your nudging matrix is. But if you remove viscosity, then you can prove the convergence. So the idea is that for geophysical equations, there is almost no diffusion. For instance, for weather forecast, it's Euler's equation, so there is no diffusion. And then people add some diffusion or use the diffusive scheme to stabilize the integration of the equation, because you have a hyperbolic system without diffusion, so it's quite difficult to solve. And the idea is that the diffusive term is not so physical. Well, you also take into consideration the subscale phenomena, but they are almost reversible too. So the idea is that if you take the original model here, so this is the standard back and forth nudging algorithm with the nudging term in the forward and backward equations. But then you would probably prefer to add some diffusion inside your model to be able to solve it numerically. And then we assume that F, the model, has no diffusive terms. So the idea of the diffusive back and forth nudging is that you solve the true model without diffusion. You add some diffusion to stabilize your numerical integration, and you add the nudging term to make the feedback to the observations. And for the backward model, it's the same. You solve your direct model, your model here, sorry, in backwards in time. You add some diffusion to stabilize the integration, and you add the nudging term. So the signs are different because this is backwards in time, but if you switch, change the time, capital T minus T, you are back to a forward equation like this, which you can compare it with the forward nudging, and you see that the only difference is that you just reverse the model. Instead of solving the model forward, you solve it backwards. But then the diffusion has the good sign and the feedback to the observations too. So just a very simple case for linear transport equation here. So you add some diffusion to stabilize the numerical integration. So for the forward, you have the forward transport stabilization with the diffusion and feedback to the observations. And for the backward, so here it's written in a forward way. So you have the, let's say, backward transport and diffusion and feedback. So in this case, you can prove that you have convergence, and you converge to this solution here, which is well, V infinite is almost equal to the observations, but then there is here the smoothing term coming from the Laplacian. So the idea is that, in some sense, the result is a smoothing process on the observations. So if there is some noise on the observations, you get something much less noisy. So is it here? Yes. So here, for instance, in red, you have the true solution, which are the observations. So you can see that there is, it's not very smooth here. So the equation is transported to the right and then backwards to the left and so on. And the blue is the back and forth nudging solution, initialized at 0. And you can see that after 2 or 3 iterations, you just get this blue solution, which is exactly the solution of this equation here. So if you take the red curve, you apply the Gaussian diffusion, you will get the blue curve. And here you have the convergence of the algorithm with the forward and backward resolutions. So you can see that the error decreases asymptotically in time. So just to show you, with a nonlinear transport, no, here it's a linear transport, but with a non-constant coefficient. So the coefficient is a sine function, and you can see that sometimes the solution is moving faster than at some other points. So still you get some good solution with some smoothing, but then it's a little bit more difficult to know exactly, theoretically, what is the equation of the solution at the end. So I think I should conclude. So the idea is that the back and forth nudging is a very simple data assimilation scheme because you just need to add the feedback to the observations. You can do it even if your model is a black box. And you can also try to solve the model backwards in time with the black box model by changing the sign of delta t, your time step. It's very, very efficient in the first iterations. It has a very low computational cost and memory cost because you just run the model and almost nothing else. You can stabilize here the backward model, but also if you have some forward model which is unstable, you can, and if you have some observations, you can almost stabilize your model with the feedback to the observations. And the idea is that probably it's a very, very efficient preconditioner for other data assimilation schemes. So for diffusive back and forth nudging, it's almost the same. It converges even faster, and you can, what is good is that you can use very small nudging coefficients because both the forward and backward model are stable, and then the correction you add is very small so that it's, it does not remove the physical part of the model. And we still have very precise forecasts. So there is still some work on this algorithm with the full primitive ocean model. So we have a PhD student that is working on that. And on twin experiments, he has very nice results, almost better than the 4D VAR. So we will try with realistic observations. So it was quite difficult with the full primitive model to solve the backward system because there was some small diffusion inside the model equations, but then with the new diffusive back and forth nudging algorithm, it works pretty well. And then you have the perspectives for both algorithms to try to correct the non-observed variables. For instance, if you know the SSH, try to correct the velocity. And try also to improve the backward nudging matrix with, for instance, some approximation of the solution of a Riccati equation. Okay. Oh, yeah.
No smallness hypothesis of data or perturbation. There is no such requirement.
Yeah, nothing.
So it's a global method.
Yeah.
Your initial guess is somewhere very far.
You have to use you have to use a small feedback if you are very far because then your feedback, the correction will be high. So you will get some oscillations. So
it will take more iterations to.
Yeah. So if you're very, very far, you should start with a very small coefficient and then you can increase it. Otherwise, you will get some oscillations, some waves in the solution.